These are the notes for Unit 5, Day 8. They start on page 25 of your note packet, and you might want to pause the video and grab some highlighters or markers. I use some color coding in this set of notes. So today we're looking at concavity, and we're looking to determine the concavity of a function, and so we're looking to relate the concavity to the second derivative. So that second derivative that determines concavity really gives the function its curvature. And so we're going to look into that and see how that is changing as we move across a function. So I've got a short video here to kind of explain just that.
Polynomial here. Here's the polynomial. I've written it in factor form, and it's graphed right here on the coordinate plane. And we want to connect the idea of concavity with both the first and the second derivative values and what's happening with them. So let's first talk about concavity. Concavity is a way of describing the curvature of a function. And one type of concavity is something called concave up. And so concave up, you can kind of think of a cup, or concave up holds water. So the part of the graph that would hold water would be this part of the graph here. So this part is concave up, just from a visual perspective. Concave down then is something that might spill water. So this part of the graph here is concave down. And so there's this location where we transition from this concave down, from the spilling, to the concave up, or the holding water. And so we want to investigate what that is. And so let's just try to connect this concavity here with the first derivative. So if we notice, let's display the tangent. If I display the tangent, that's the first derivative. And right now my A value is way down here off the bottom of the screen. So I'm going to slide my X coordinate, and you can see the point come into the picture now. And so we can see that right here, the tangent line is quite vertical. The tangent's value, this is MT1, which means the slope of the tangent. This is 18.58. I also have it written out here. So we have a slope of 18.58. And if you notice the derivative when we're concave down, if you notice this derivative value change, as we move the point through this domain where we are concave down. So it's right now the derivative is 18.58. And when I keep moving the point, it goes to 16 to 14 to 12, 11, 7, 6, 5, until we get to this hill here. And we know that at the top of that hill, and it doesn't look like I can hit the top of the hill exactly, but the top of the hill should have a derivative of 0, or pretty close there. And then I continue, and see my first derivative is now negative, okay, during that time. So if I back this up here, notice, let's run this again. My derivative is going from big and positive to 0 to negative. So my derivative is decreasing. So that is the definition of concave down. The definition, if you look and you notice, is an open interval I. If the value of the y prime, which is the derivative, is decreasing, then we're concave down. So watch the derivative now continue in value as we reach this point where we transition from concave down to concave up. As we transition from concave down to concave up, notice my derivative value, my first derivative, is negative 4.46, negative 4.49, then it goes negative 4.5, and then it goes back to 4.49 and back to 4.46. So if we notice that change occurs about right here, that is as steep of a tangent line as I can draw there. So at this location, notice my second derivative is basically 0. Okay, but we're focusing on the first derivative here. Notice now my first derivative is starting to go from negative 4.5 to negative 4.49, negative 4.06. So now my first derivative is increasing. Then it's going to be 0 as I get really into this valley here, into that minimum. I should be able to get that to be exactly 0. And then I turn the corner and my derivative starts to become positive. So if I back this up here, let's start back here at this point of inflection where we change our concavity. We see that our first derivative goes from negative to basically 0 to positive. So our first derivative is increasing. And if you look at your notes, that is the definition of concave up on an open interval I if the value of y prime, which is the derivative, is increasing. So those are the derivatives. That's kind of what it looks graphically. If you notice, it was at this location here that we maximized our magnitude of our slope. In other words, we have the steepest line possible. It's also where the second derivative is equal to 0. And we call that the point of inflection. So now let's take a look at, let's back this all the way up. Let's take a look at the second derivative and what the second derivative is doing. So if we relate concavity to the first derivative, we talk about the first derivative decreasing when it's concave down and increasing when it's concave up. Think about that. The second derivative is the derivative of the first derivative. So when we're concave down here, if my derivative is decreasing, that means the second derivative must be negative, right? Because the second derivative is the derivative of the first function, of the first derivative. So if your second derivative, that's the derivative of this, and this is getting smaller, then this must be negative, causing a decrease in the first derivative. So for concave down, my second derivative, now I'm focusing on this number, my second derivative is negative because I have decreasing slope. And then when I go to my point of inflection and go beyond my point of inflection, my second derivative is now positive. And I'm in the concave up area where my slope is increasing, which is why my second derivative is positive. That's going to cause an increase in the slope. So that's connecting the concavity to both the second and the first and the second derivative.
Let's diagram this into our notes. I have the grammar involved in this curvature of this function. So this highlight here, this is the region where we are concave up. We think of when we are visually identifying concave up, we're looking for something that looks kind of like a cup that would hold water. And then this is the area where we are concave down. So this looks like something that would be spilling water, kind of turning the cup upside down. And so when we're talking about where we transition, where we change from concave down to concave up, we call it a point of inflection. And that is the definition of the point of inflection. It says point of inflection here is the point on the graph where the function has a tangent line where the concavity changes sign. Okay, so we talked about the point of inflection having a second derivative of 0. And since we're changing sign, that means we're changing from concave down to concave up. So the second derivative in this particular instance, the second derivative is changing from negative to positive. We could also have a situation where it changes from positive to negative. So if we look at this black line here is a tangent line, just like in the animation. And so we know we have a fairly steep positive slope here. And so as we go across the domain in this part of the domain where we're concave down, we go from a positive slope to 0 slope as we hit this maximum, then to a negative slope as we hit that point of inflection. So if we're going from positive values to 0 to negative values, that tells us that our slope or our y prime is decreasing in value over that interval. That is the definition of concave down. And then as we said in the video, that's further proven by the fact that the second derivative is negative over that domain. As we continue into this part of the domain where it's concave up, we start at this point of inflection. We have a negative slope here. Then we go through and hit this minimum where we have zero slope. And then we, on the other side of that minimum, we have positive slope. So if our slope is going from negative to 0 to positive, that represents an increase. So our slope, or our y prime, our first derivative, is increasing on that interval. That's the definition of concave up. And we further have that supported here in the second derivative by showing that the second derivative value is positive, which is what is causing the first derivative to increase. So that is the those are the terms associated with this sort of associated with discussing concavity. So let's do since we kind of approach this graphically, let's try this graphical question here. We have a graph here, and this is the graph of the derivative now. So it's different than what we've been looking at. So if this is the graph of the derivative values, when we talk about increasing and decreasing derivatives, we're talking about looking at these values specifically. And when we're talking about positive and negative derivatives, in other words, positive and negative slope, we're looking at like what quadrant we're in. Are we up above the axis or down below the axis? So let's read the stem here. The figure shows the graph of the derivative of a twice differentiable function. That just means we have a first derivative and a second derivative. And we're going from -3 to 4, that interval. The graph of f prime has horizontal tangents at -1, 1, and 3. So it's got a horizontal tangent here and here and here. On what open interval contained between -3 and 4 is the graph of the function, both concave down and decreasing. So we don't have the function. We don't really know what it looks like. So we're going to have to rely on what we know about the first and the second derivative to find these domains. So, so that's why we are calling this connecting concavity to the first derivative. So here's our definition of concavity. You have this in your notes. In this problem, we're looking for concave down. So concave down, we know, is where the derivative is decreasing. So here's our derivative. So if you think about this, right, we have a function f. Here's the derivative of that, which is also itself a function. And then its second derivative would also be a function. So we can look at this. We can look at this the same way we just look at functions. We're looking for where y prime is decreasing. Well, this is y prime. This is the graph of the derivative, and decreasing means it's going down in value. So pause the video for a second and think to yourself, where on this graph are we decreasing our values? Okay, so if you're tuning back in, actually, before we reveal those domain locations, what you should be doing is highlighting that, highlighting where the derivative is decreasing. So taking a look at that, the derivative is decreasing here. So we start at a high value and go to a low value. And it's also decreasing here. We start at a high value and go to a low value. So that's where the derivative is decreasing. And so those are the locations where the actual function is concave down. Okay, now the second part of this is looking for where the function is decreasing. Okay, so the function is decreasing when the first derivative is negative. So if we think about this being the first derivative, we know that we have positive values in quadrants 1 and 2 and negative values in quadrants 3 and 4. So pause the video again and highlight where, based on knowing the first derivative, highlight where the first derivative is negative. Okay, so if you're viewing this part of the video, you've already tried this on your own. So the first derivative is negative right here, right, in quadrants 3 and 4. So we want both of these to occur simultaneously. That's what the stem is saying here. So we got to look for where they overlap. So where does the green and the pink overlap? Well, the green and the pink overlaps everywhere where you see brown, which means that they overlap here. So we are both decreasing, and our derivative is both decreasing and negative. And here, again, our derivative is both decreasing and negative. So those are the locations, and that the function itself is concave down and it's decreasing. So it's on the intervals of -2 to -1 and 1 to 3. So that's answering the question. And then the justification is where the second derivative is negative, less than 0, and the first derivative is negative. And you could have also said this is where the first derivative is decreasing instead of this. So you could have substituted in this statement for right here as well. So let's take a look at another question. Question 2 talks about a point of inflection. So we've got to set up a method to find these points of inflection and then verify them. So if you remember back to the definition, point of inflection is where the second derivative is either 0 or undefined, and then and I capitalized it, it's a big and your second derivative has to change sign. That's where we have a point of inflection, because the changing of the sign is the changing of the concavity. So first thing obviously we need is the second derivative. The second thing then is we're going to set it equal to 0 and solve. And then we're also going to look at the derivative and look for locations where it doesn't exist. We have an example of each variety in these notes. And these are possible points of inflection, possible. We don't know until we set up a number line. And we put those points of inflection, those possibilities on that number line, and then we start checking values on either side. So if this process sounds familiar, we did all this exact same process with the first derivative to find our extreme, our mins and our maxes, and our cusps and our corners and all that stuff, our hills and valleys, cusps and corners, which are all generally minimums and maximums. And then the next one is the identify the intervals as positive or negative. So that's that charting that we do. And then look for sign switching on that positive and negative chart. And then you can label that point a point of inflection. So just to kind of refresh our memory here, because it's off the screen, point of inflection is when the second derivative is equal to 0 and it changes sign. So we need that second derivative. So here's the first derivative, 15x to the 4th plus 40x cubed. Here's our second derivative, 60x cubed plus 120x squared. So we've got the second derivative. Now we're going to set it equal to 0, and we're going to solve it. So with polynomials particularly, we know that solving process is factor and set those factors equal to 0 and solve for the points. So we are going to factor a 60x squared out. That leaves us with an x plus 2. And then we'll set each one of these equal to 0. So 60x squared equals 0 means x equals 0. And x plus 2 equals 0 means x equals -2. So there are our two possibilities. Now I've run out of space on the screen, so I'm going to switch screens, but this whole question is going to be located at the top. All right, so now to move on, we've got the possible points of inflection. We're going to sketch that number line. So here's our second derivative number line. Very important to be sure to label it, so that because many times we're doing first and second derivative number lines in the same question. So we want to label this and identify it as a second derivative. We're going to place -2 and 0 on our number line. And now we're going to test each of these domains. I'm stepping away from the math involved and just making a determination on positive or negative. So let's start out here at -3. So f double prime of -3, right? When we want to know our concavity, we need to find whether the second derivative is positive or negative. That means substituting -3 into the second derivative. I'm going to choose to put it in here because the factored form is easier to determine whether we have a positive or a negative answer without doing math. So if we notice we have 60x squared out here, so whatever we put here, it's always going to be positive because we're squaring it. So we know we have at -3, we have a positive value, and then -3 plus 2 is a negative. So a positive times a negative is a negative. So we know in this domain, we are we have a negative second derivative, which means we're concave down. Let's try between these two locations at -1. Putting -1 in here, we've got a positive and a positive. So positive times a positive is a positive. So this domain, we have a positive second derivative, which means we're concave up. And let's try out here at 1. Sticking 1 in here, we get positive and positive. So positive times a positive, we are concave up in this domain. So we have to look for second derivative equal to 0. We know that's right here and here. And then we have to look for sign changing. And we have a sign change right here. We go from negative to positive. So this is a point of inflection. At this location, we go positive, positive. That's not a point of inflection. So we have a point of inflection occurring at -2. And now our justification is to say exactly this. Okay, the second derivative changes sign from negative to positive. So I chose this portion to justify. There's a lot of ways you can say this. You can say something like f double prime of -2 equals 0, and f double prime changes from negative to positive. Or you could say f double prime is negative for values less than -2 and positive for values greater than -2. There's a lot of ways you can reword the justification. Okay, question number 3 is another algebraic solution. Same type of question. We're looking for points of inflection, which means we need the second derivative. So the first derivative, just a quick reminder here, we have a fractional power. So we're going to bring that power down, and subtracting 1 here is like subtracting 3/3. So our new power is -2/3. And then the second derivative, we're going to bring this fractional power down and multiply it by the coefficient. So we get -2/9. And we're going to subtract 1, which is like subtracting 3/3 again. So our new power is -5/3. And we know that anything to a negative power really should be relocated in this rational setup here. So we really know that this is in the bottom. So I'm going to rewrite it to stick it in the bottom. So this is one of the scenarios where we don't have anywhere where the second derivative is 0. In order for the second derivative to be 0 with a rational expression, we'd have to be able to get the top to equal 0. And we can't because the top is 2. But we do have a location where it's undefined. And that requires looking at the denominator. So we know that the second derivative is undefined when x is equal to 4, because that will make the denominator 0. So we have a possible point of inflection at 4. So I mentioned a little earlier that I was going to have one of each of these, right? Where we were looking at second derivatives equal to 0, and one where we were looking at second derivatives that were undefined. And this is obviously the undefined one. So we're going to set up our second derivative number line. We're going to identify x equals 4 on that number line. And this is a possible point of inflection, so we need to verify what's happening on either side. So we'll plug in something littler than 4. I just chose 0. 0 is nice to work with. If we put 0 here, it makes this negative. Negative power, a negative number to an odd power is still negative. But you have to remember that you got a negative sign out here. So we have a negative times a negative, which is a positive, which means we are concave up for values that are smaller than 4. Let's take a look at the other side of 4. I chose 5 because it makes this a nice number. It makes it 1. So 1 to an odd power is still 1, or a positive number to an odd power is still a positive number. Don't forget about this negative out here. It's really common with fractional powers when we have functions like that. We get into negative powers real quick, as you can see. So we have a positive times a negative, which is a negative. So we know we are concave down for values of x that are greater than 4. So we have a point of inflection here because we change from positive to negative. So we can give our answer of point of inflection occurs at -4, and then we can give our justification. And again, we can say, we can restate this several different ways. We can say that the second derivative changes sign at that location. But we have to make sure that we say we know it's changing from positive to negative, and gives further proof that you know what you're doing. Or you could say, that our second derivative is positive for values less than 4 and negative for values greater than 4. So there's a couple of ways you can state that justification. Okay, so here's another graphical example. And here's an example where we give you the second derivative. So if you think about this, when we talk about the second derivative, we talk about where the concave up and concave down. And we know that concave up is a positive second derivative, which would be everything in quadrants 1 and 2, because this is where all these values are positive, and these are all second derivative values. And concave down would be the domain locations where we have negative second derivative, which would be everything in quadrants 3 and 4. So just to kind of give you kind of your bearings, it's hard to look at these graphs when they're not functions. When they're derivatives, you got to kind of pause and take stock of what you know. Okay, so the stem says a second derivative of a function f is given by f double prime is equal to the product of these factors, x times x minus y, a times x minus b squared. The graph of f double prime is shown. For what values of x does a graph have a point of inflection? So we know if this is factored form, then we have zeros, right, at 0 and a and b. So they've just arbitrarily said here's a, and here's 0, and here's b. And so a 0 here, here, and here means the second derivative is equal to 0. So those are the possible points of inflection. So we have this and this and this as our possibilities. That would be the same as setting this equal to 0 and solving, right? We get x equals 0, x equals a, x equals b. Now we have to look for the sign change. Well, sign change means, am I going above to below or below to above, or am I not doing either of those things? Because these are the second derivative values. So let's take a look at a first. If you notice at a on either side, this is like just like our number line, we go from above to below. So we go from a positive second derivative to a negative second derivative. So a is definitely a point of inflection. Let's look at 0. We go from I guess I'm doing the justifications as I go along. So we do have a point of inflection at a because the second derivative changes sign from positive to negative there. Let's look at 0. Before 0, we have a negative second derivative. After 0, we have a positive second derivative. So yeah, I'm looking at these as quadrants. We're on the third quadrant, which is negative. We're up in the first quadrant, which is positive. And these are second derivative values. So again, at 0, another point of inflection because we change from negative to positive at that location. And then we're going to look at B. So at B, we're up here in the first quadrant, we have a positive second derivative, and then we have another still positive second derivatives. So we don't have a sign change there. So we have no point of inflection there. We just have a situation where we have a concave up and still a concave up scenario. So that we're going to rule that one out. So we have points of inflection at a and 0. And then we have to justify it. And we have to justify them separately because we have different things happening at each one of those locations. So when we get into the classroom, we'll go over the takeaways from the notes, and then we'll work on the topic questions and get you through that gradual release onto your homework.